So welcome, everyone. My name is Gyula Fora, and as introduced, this is my colleague, Matthias. We're part of the Flink engineering team at Cloudera, and we're working together with Marton and some other folks at Cloudera to bring Flink to the Cloudera platform. Today, we're going to focus on a very Flink-specific topic, and it's about configuring Flink streaming jobs for production applications. So the most important thing I would like you to take away from this talk is that you should always try to aim to keep the configuration as simple as possible. It almost never helps to overthink this whole configuration problem. Flink works extremely well out of the box. So you should really only touch a few config options that will actually make things better, and only if you know what you're doing. Otherwise, you're going to cause yourself trouble in the long run. Maybe you will not see it in a few days, but it might come back and haunt you in like a few months down the road. And always, it's better to start a job, get some experience running it, see the performance characteristics before actually touching any knobs to tune the performance. So in this talk, we will touch on a few separate topics. I promised a lot of things in the abstract. We might not cover everything, but we will try our best. So first, we will talk about resource configuration, such as configuring the memory and parallelism of your application, and also some Yarn-specific configuration options that are important for long-running apps. We will look at how Flink is integrated in the Cloudera Manager, and how the Cloudera Manager and the Cloudera platform can help you to get the most out of your Flink jobs, and how the configuration story fits into that. We also look at checkpointing and state backends, which is one of the most crucial components to understand when it comes to configuration. And lastly, we will also look at how security works in Flink, how Kerberos and TLS can be configured in the context of a Flink application. During these sections, I will not show too many config option names and like config keys, but at the end of each section, there will be a page to recap the configuration recommendations for that section, so that later you can come back to the presentation and look at those slides to remember. So let's start with resource configuration. This is the first thing that hits you when you want to deploy a Flink job. You have to make a decision on how much memory and parallelism you want to allocate for your Flink job. So it's more of a question is how much is enough, how much is too much maybe. A good suggestion is to always be conservative with the parallelism of your job. It's better to start with something small. It's always easier to increase parallelism later than to start a job with a very high parallelism where thread contention might be the bottleneck, and it's going to take you forever to realize that you actually need to scale down instead of scaling up in certain cases. You should also be generous with memory, on the other hand, because more memory never really hurt an application. So if you can afford it, it's better to be on the safe side. But you should always monitor back pressure of your application and GC stats. Not monitoring the GC stats close enough have lost me probably several weeks of development and debugging performance problems, because it just took too long to figure out that it was an actual memory problem. One thing that you should always set when you run Flink application is the max parallelism of your application. Flink comes with a default setting of 128 for smaller parallelism jobs and some higher number for larger jobs. But first of all, it's important to understand what max parallelism means in the context of a Flink job. So on one hand, it means what the name suggests. It's the maximum possible parallelism to which your job can be scaled up when you change parallelism after you have run the job. So you take a save point, increase parallelism, and restart the job. So this is the max parallelism setting that you can set. It also sets the number of key groups that the Flink job has, which is basically a state partition. And this will determine how data is distributed between shuffle operators. So what this means, if the key groups are not distributed evenly between the Flink subtasks, data will not be distributed evenly. So you should always aim for a max parallelism combination where the max parallelism is divisible by the parallelism setting. So from this, it naturally follows that you should aim to select a max parallelism number that has a lot of divisors, so you can change parallelism settings without ending up with an uneven key distribution. So good numbers to pick for max parallelism are factorial numbers like 120, 720. But if you search in Google for highly composite numbers, this is the mathematical term for numbers with a... Sorry? Was the mic off?
Yeah.
Crazy.
But it was OK. Never mind.
Yeah. So now I have to talk more quiet. Yeah. So search for highly composite numbers. Those are numbers that will be good for max parallelism. As for getting an initial parallelism estimate, you can kind of go from your input data rate and the kind of job that you're running. For stateless jobs, you can kind of assume that your every Flink instance can consume at least like 1 million records. It might be more, might be less, but that's a good estimate. For in-memory state, maybe a little bit less, and for RocksDB state, even less. These are good numbers to start with. Estimate your parallelism based on this, and then you iterate to fine-tune it based on your hardware configuration and your application complexity. Another question that comes up again and again in the context of throughput is the throughput versus latency trade-off. Most people tend to think that this is like a deeply rooted trade-off in the stream processing systems, and it might be technically true, but in reality, for most applications, it's not really a trade-off, but we're actually building pipelines and adding operators that reduce the throughput and also increase the latency. So in many cases, we're affecting both of them without having any trade-off, really. So for instance, when we increase our pipeline complexity, or we choose RocksDB instead of the heap state backend, we decrease our throughput and increase the latency, so we get worse on both. Same with windowing applications, including windowing semantics, where latency is not even a consideration, but still people try to think about it when it doesn't make sense. The only configuration option that I can recommend you tune for certain cases is the buffer timeout in Flink. So the buffer timeout, what does it mean? Flink uses network buffers to transfer data from one operator to the other. So basically, the upstream operators put data into these buffers, and when these buffers fill up, they're transferred downstream. And if the buffer doesn't fill up completely in a certain time, then these buffers are transported half full anyways. So with high data rates, this timeout is never reached, so it doesn't really matter for latency. But in certain cases where we have a low data rate and a high buffer timeout, it can happen that the buffer timeout is actually reached. Thus, it controls the latency, the maximum latency of our application. So for lower data rates and very low latency requirements, we suggest to set the buffer timeout accordingly. It can be configured in milliseconds, so you can say, instead of the 100 millisecond default, I want a buffer timeout of 10 milliseconds. Yeah. Of course, here is an actual trade-off for throughput and latency, because the less you wait, the more incomplete buffers you might send, so you reduce your throughput. But it's not a big trade-off as long as you don't decrease the buffer timeout to 0, which would mean you send each record individually, which would severely hurt performance. So we recommend you never to do that. So that's all about parallelism, throughput, and latency. As for deploying it on Yarn, you have to make sure that your job is not killed either by Yarn or by itself. So so Yarn will kill any application that reach the memory limit that is set for the container. So we have to keep in mind that when we configure task manager size on Yarn, we actually configure the Yarn container memory limit. And this doesn't mean that the task manager will get so much heap, because the task manager container size has two components. It's the task manager heap and an additional memory cutoff amount that is reserved for non-heap memory usage of the container. So we have to keep that in mind. Also, we should always use a Yarn queue which doesn't have preemption enabled. Preemption means that Yarn can kill these applications or containers in favor of other applications with higher priority. So this is the Yarn side of things. From the jobs perspective, we have to set failure limits, like how many failures can the application tolerate. There are two settings that control this. One is the maximum number of failed containers. So we suggest to set this in proportion to the total number of task managers that we start. So if you start 10 task managers, then you can set 30 as the maximum number of failed containers, so every container can fail a few times before shutting down the application. And also there is the setting for maximum number of app master failures. This should probably be a lower number because it controls how many times the job master should fail. Of course, this might happen, but it probably if it happens too often, that is a bad sign, so you should look into it. So as I promised, for this section, we have a rundown of the configuration settings that we suggest. You can always come back to the slides later. It will be available online, and check them out.
OK, so Gyula has mentioned a few configuration parameters already, why you have to tune this. And I'm trying to show how you can do this in our platform. So Cloudera Manager is a centralized console of our data platform stack that is responsible for deploying and operating the services on our platform. As you might have heard in the keynote, our platform can run on-premise or in a cloud, in physical or virtual machines. And basically, the Cloudera Manager is responsible to create a cluster out of those machines and deploy the binaries there, install services, and then operate and monitor the software stack there. So once you have a cluster that is managed by Cloudera Manager, you deploy the binaries on a cluster. We ship the binaries in a special distributing format. It is called parcels. So once you have the binaries in place, you have to pick the services you want to run on your cluster. In this particular example, along with Flink, I've choose HDFS Yarn, Kafka Schema Registry, and Zookeeper to install, but you can choose additional services on a cluster as well. Once you have your services selected, you have to set some default configuration. So Cloudera Manager helps configuring the services by suggesting some default configurations. Some of the configurations are equal or matches the Apache default. Some other has or being changed by Cloudera Manager based, for example, the cluster size or your host specification. Your host can vary different, can contain different number of disks or number of CPU cores, amount of memory, and so on. So when you when you're trying to distribute these resources between the services, Cloudera Manager provides a coarse-grained tuning for that. So you can set a certain amount of percentage to each service from the cluster resources. And then as you put more production workload on a cluster and monitor a cluster, you can fine-tune it later. Also, Cloudera Manager from the beginning can create service configuration to integrate your services with centralized security infrastructure like KDC or LDAP. And once you have your services up and ready, Cloudera Manager is responsible for monitoring all the processes on a cluster and resources, create alerts based on several triggers that you can have and that you have configured on a cluster. This is the homepage of Cloudera Manager. This screenshot was taken by the Flink history server. This is one of the long-running daemon servers of Flink that we currently have in our stack. The jobs basically are just yarn jobs that are submitted. They do not require any long-running processes, so only the history server at the moment is being managed by Cloudera Manager. The job requires only client configuration, and I will show you how it is handled in the upcoming slide. This is an overview of a general process page. You can see the status of the process all the time, also the state history. So if any of your processes has been killed or died for some reason, you can always look at the status, look at the timestamp when the service went down, so you can dig into the role logs by this timestamp easily. Also, the role logs available from this console, the web UI also accessible for here. So everything that is related for the full lifecycle management of your processes are put together in this nice web UI. Next slide is the configuration page of Flink. This is related to RocksDB, state backend. A few common parameters are basically already added in Cloudera Manager. You don't need to add everything in this web UI. There is a concept so-called safety valve. So any new services that you want to configure, configuration parameters you want to change or add can be added without basically handling it with a web UI in a form like this. I already mentioned that the Flink jobs do not have a long-running process. They require only a so-called client configuration. And the client configuration is basically contains the Flink configuration YAML file itself, log4j properties, and they are deployed with this gateway role. The Cloudera Manager differentiates two roles, the gateway role and the server role. Server role contains the configuration plus a running process, like the Flink history server, and a gateway role is just a bunch of configuration that Cloudera automatically deploys first time or when you change it on the console on those hosts where you deployed the gateway role. So I'm going to hand over to Gyula to continue with the RocksDB stuff. Thank you.
Yeah. So now we've seen the icing on the cake. So how nice is this to configure Flink and the Cloudera Manager instead of working with the YAML files? But still, the main problem remains. What do we actually set? So state and recovery and checkpointing configuration is one of those topics which I would say requires the most expertise and most experience of running Flink over time, especially if you run the RocksDB state backend. So our primary goal with configuring checkpointing is so that it has minimal impact on our application. Checkpointing itself doesn't add any functional value in our application logic. It should only be there in case a problem happens. We want to be able to recover quickly. And we want to be able to do this for any amount of state that we have in a reasonable time. So there are a few things that we can play around with to achieve this. Some of them can be configured programmatically through the stream execution environment. Some of them are shared parameters between state backends. And then there is the obvious problem of which state backend we choose and how to configure any given backend. So let's tackle the simple ones first. As I said earlier, you should always configure max parallelism. It affects checkpointing and everything about your job. You should also set the operator UIDs of your Flink operators, at least for the stateful ones, but I recommend you set it for all of your operators, because you might miss a stateful one, and then you're going to give yourself a lot of headache on recovery when you change your pipeline. You should always consider setting snapshot compression. This can be enabled through the execution config, which will allow Flink to compress the save point data, and then, depending on the backend, the checkpoint data as well. And it can reduce network traffic, and depending on your setup, it might greatly reduce the recovery time. As for the Flink configuration, I suggest you always enable local recovery. What this does is, in addition to storing the checkpoints to the distributed storage, your Flink application will also keep a local copy of it. So on recovery, it can just pick it up from the local disk instead of having to copy it from the network. It can save you a lot of trouble, and it will greatly reduce network traffic spikes during recovery. This is especially important when you have some like cascading failures of different applications. It might put you in a very bad situation if everybody tries to copy back, I don't know, 200 terabytes of state from HDFS at the same time, and yeah, they expect to recover quickly. One thing that is often overlooked is the checkpoint and save point directory configuration. Most people just set the directory that is shared for Flink, and then you get these random subdirectories with the job IDs or application IDs there. And yeah, this is fine when you start, but 2 years down the road, you will end up with this HDFS cluster full of checkpoint directories. Some of them are used by Flink jobs, but it's hard to tell. And some of them are garbage, so you have to come up with some scheme how to delete things without ruining your running jobs. So I suggest you always set something that is specific to the pipeline that you're running. So if this is a ride-sharing app, then you put checkpoints, ride-sharing, and you're going to have an awesome time when you have to clean up all the state. You can just delete the whole thing and not have to worry about destroying other jobs. So the interesting topic of checkpoint configuration is, of course, selecting state backend. The default in Flink is the heap state backend, checkpointing to a file system. But the other production alternative that people commonly use is the RocksDB state backend, also checkpointing to the file system. So heap and RocksDB doesn't mean that the actual checkpointed state is stored on heap or in RocksDB. What this means is that when the job is running, the live state is stored either on the Java heap or on RocksDB. So what's the difference between these two? So the heap state backend, as it stores deserialized data on heap, is super fast. It doesn't require any tuning. There is no knobs to turn. So as long as you have enough memory, it's going to give you a very pleasant experience. This is the default state backend. So you should always try this out first. It provides a pretty straightforward resource control, because you set the JVM heap size, and that's how much state you can keep. Of course, this is also the limiting factor about the usage of this backend, because if you run out of memory or with large heap sizes, if you have problems with garbage collection, it's kind of hard to go around it. maybe that's just how much memory your machines have. And also, it doesn't support incremental checkpoints at this point, but that's not a big problem because checkpoints happen asynchronously. But that's an aspect that I had to mention. On the other hand, you have the RocksDB state backend, which stores the state in embedded RocksDB instances. RocksDB is an embedded database. It stores part of the data in native memory, and part of it is stored, and most of it is stored on disk. It scales, since it stored the data on disk, it scales to terabytes or even more state seamlessly, as long as it's configured properly. And it also supports incremental checkpoints so that the checkpoint sizes and the network traffic during checkpoints is very low. But there is a lot of downside to RocksDB. Ideally, it needs a fast disk, so an SSD, and a very good configuration, which is far from trivial. If any of you have used RocksDB, you probably know it. It uses native memory, so we have to account for the RocksDB usage outside of the task manager if we run in containerized environments where strict memory limits are enforced. And it is, of course, pretty slow compared to the heap state backend, but it's still pretty quick compared to anything else that you might try. So it's kind of like the second best. It's not really the second worst. Yeah. So I don't want to talk about the heap state backend anymore, but I think we need to look into the RocksDB a bit closer, at least to look into the memory usage. So in order to understand how RocksDB uses memory, we need to understand how Flink uses RocksDB. Each stateful operator subtask has its own embedded RocksDB instance. So if we have a pipeline with 8 parallelism and 2 stateful operators, such as some keyby state and some window, that would mean we have 8 times 2 RocksDB instances, so 16 RocksDB instances. Each of them use the same configuration as it is configured globally, and each of them will store some state and use some native memory. I mean, of course, how much memory each of them consume will depend on how much key they have, but that's the rough picture. So the memory configuration of RocksDB is a bit complicated. There's several articles and wiki pages about this topic. And if you're considering this for production use, you should at least have a rough idea about it. To give you a general idea, there are 3 main sources of native memory usage in RocksDB out of the box. So the first is the block cache. RocksDB stores data in blocks when it writes them to disk. So when you read something from disk, RocksDB will read that block and put it in a block cache for fast read access. So it's basically a read cache of the blocks. For the blocks that it has written, it builds some indices and Bloom filters. These usually live in memory. This is necessary for fast data access to know where to look up the data on disk. So this is the second category. Block cache is fixed size. Indices and filter sizes grow as the amount of data that you store on disk grows. So that's another complication. The third source of memory consumption is memtables, which is the place where RocksDB writes new modifications to the database. So it's basically like the first level cache of the embedded database. So out of the box, we have to configure these 3 aspects of RocksDB to control the memory usage. But people tend to fail, and we have at King we have run RocksDB in production for several years, and at the end, in the beginning we tried to figure the memory consumption out. At the end, we turned off physical memory checking in Yarn, and we kind of let RocksDB free roam the machines, because It mostly doesn't cause troubles, but we also couldn't fix the configuration in a way that it's both has a good performance and it stays in the box. Fortunately, there are some new changes coming to Flink with some newer RocksDB features. It is called one new feature that is hopefully coming to Flink 1.10 is the RocksDB write buffer manager. It's a RocksDB feature, but we enable it in Flink by upgrading the RocksDB version. This will allow us to put the mem table usage in the block cache as well. And there has already been an option in RocksDB to put the index and filter usage inside the block cache. So basically, now with the write buffer manager, we complete the picture and can control the memory usage of RocksDB by controlling the size of the block cache. There's still some tuning remaining here for performance, but at least we have a good grasp on the memory usage. This is not the write buffer manager is not yet available in Flink. It's still under development. We have in our Cloudera fork of Flink, we are also experimenting with it, so maybe you get to try it soon. Yes, and here are some of the config options that I mentioned. As I said, come back later, check it out, and yeah. So yeah, now we go over to our last topic, the most exciting one, security.
Yeah, so configuring security in a distributed environment can be a challenging task. Before joining the Flink engineering team, I spent a few years in professional services as a solution architect, and I've done manual security integration too many times. So now is the time for me to improve this process. And in the last few weeks, we've been working on these features in our stack. So I'm not going to cover everything today from security. I'm going to focus on those topics that has been integrated in Flink as well. So namely, authentication and encryption. From authentication, it's basically a Kerberos. Kerberos is the strong authentication solution in a distributed environment, and TLS is the standardized encryption solution for services. So authentication. Flink provides some integration for Kerberos authentication for a few connectors. I listed here. It's basically HDFS, HBase, Zookeeper, and Kafka. And those are the security modules that are responsible for integration. And the last one, the just security module, can be used not only to integrate the Kafka connector and provide Kerberos authentication for this connector, but also additional components that also implement the Jest security module can use this feature. And you can see on the right side of the slide, by simply adding a configuration, you can enable new services automatically, new connectors for your application that relies on Jest security model. In Cloudera Manager, we are trying to set global defaults for most of your job, but it's not always possible. If you have a technical user who submits Flink jobs, you can generate a single key tab to that user and use only one principal for that. But if you have multiple users, usually each user has their own principal and a corresponding key tab. So hence, I suggest to set these parameters on a command line. We must mention here that it was not working when we tested it in the upstream version. So Gyula and I have been ironed out this configuration, and now you're able to define the key tabs and the principals in command line. This is a more resilient solution in production. These are the corresponding Kerberos configs to manage. Yeah. Usually, you use key tabs for long-running jobs. The key tabs make sure that once your Kerberos ticket expires, you have an encrypted file that you can use to renew the key tab before it happens. They set usually 80% before the expiration time to renew your tickets. If you use the ticket from your host, someone has to log in and renew it for you. This is not happening in production environment, hence it is recommended to always use key tabs in production jobs. TLS. TLS is a little bit challenging in Flink, or at least I found challenging in Flink. Flink distinguished two types of TLS encryption, internal and external. It protects the internal connectivity by TLS as well. And this means that RPC communication, the data shuffling, and also the blob store is protected with TLS. And this is an internal TLS solution. There are no host verification, and the key store itself that contains the certificate is usually used as a shared secret, so can be submitted with your Yarn jobs. And as you see, creating a key store that can be used also as a trust store is just one command. So you can do this and before you actually submit your job. The external connectivity is also protected by TLS. Configuring external protection is not that straightforward because browsers also access the external endpoints. So, for example, if you want to log into your Flink console that is protected by key store, you have to somehow trust that certificate, and so the signing certificate that is installed usually in a trust store has to be also installed in your browser. If you're super lucky, this has been done automatically by some infrastructure guy during the cluster provisioning or by Cloudera professional services. If not, then you need to generate the key store and a truster on your own if you want to protect the external interface also with TLS. These are the commands, at least, you have to run to create a truster and a key store. I found it, challenging, but this is the standard way. So at least this is standardized. So there is no magic happening here. You just need to make sure that you generate the certificate and the keeper on every host, and then sign it with a trusted authority that is installed on your browser. Things gets complicated if you have hundreds or thousands of nodes, which is a common setup on our platform. So it's better to somehow automate this functionality, either creating your own cert toolkit or leverage our latest feature from Cloudera Manager. So this is how it works now in Cloudera Manager by the function of auto TLS. And also enabling Kerberos authentication is supported by a wizard, so it's a single-click solution in Cloudera Manager. Cloudera Manager can generate the keys, the key store and a trust store for every service, and it makes sure that that the secrets are protected and isolated from each other for every service. So again, the configs to remember, there are a bunch of them for TLS. So these were the built-in solution for security. If you want to run any other third-party connector, it is recommended to put all the configuration that related to security next to your business configuration, basically, and somehow process them automatically in your application. I have given an example how I configure the Kafka TLS from the application. You see, I prefixed the properties here and then automatically forwarded to the Kafka consumer in my application code. So at the end of the day, you only need to pass an application properties that contains all the configuration for the security as well. So thank you very much for your attention. This is what we wanted to basically cover today.
All right, I think we're out of time for now, but thank you very much, Gyula and Matyas.
Thank you, guys. Bye.